So these types of questions, I know I've mentioned before, these are the types of questions that drive me insane because I can see like 2 or 3 answers that both are like, I mean, is this definitely incorrect? Is it maybe incorrect under certain conditions? And so this and that. So there are some of these that when you see the correct answer, you might be like, oh, I wasn't sure if it was this one or that one, and I went with the other. So I bet a lot of you are going to be in that boat. So if we go through, let's just read it. In all normal distributions, the mean and the median are equal. So because normal distributions are unimodal and symmetric without outliers, the mean and the median will be equal. This one is correct. So it's not that one. So a normal distribution is completely determined by 2 numbers, its mean and its standard deviation. That's correct. If we have those 2 numbers, we know everything we need to know about that. All bell-shaped curves are normal distributions for some choice of mu and sigma. This is I'll go ahead and tell you, this is the correct answer. I'll come back to it though, because the most popular answer was D. Virtually all the area under a normal curve is within 3 standard deviations. And that's what we learned from the empirical rule. It doesn't say all, but it says virtually all. And we know that 99.7% of all of the data is going to fall within 3 standard deviations because we have our 68, 95, 99.7 rule. We call the empirical rule. So if you can think about that, it's telling us it's a normal curve. So therefore it's a normal distribution. So yes, you will find 99.7% of the data, all of the area. So there we go. Standardized scores have a normal distribution only if the original distribution is normal. And that's true because all we're doing is transforming the data. And so if we had a skewed distribution and then we converted all these into the z-scores, maybe it condenses it horizontally a little bit, but it's still going to be skewed and maybe it shifts it over. But maybe we end up with something that looks like this. So it's more condensed, but it is still a skewed distribution because every point is going to be turned into a z-score, but it doesn't change the relation between the points. So the correct answer is C, because there are bell-shaped curves that are not normal distributions. We're going to learn about one called a t-distribution. We've already learned about the binomial distribution. And the differences between them are very slight, especially in certain cases. There's almost no difference between them, but they are technically different distributions, and we need to just be aware of that. So just as a quick reminder, and I want to keep reinforcing this point, a sampling distribution is essentially just a normal distribution, but it's made up of all of the sample statistics from a certain sample size from a population. And when you pull out a specific data point, you're pulling out a mean or a proportion that came from a sample. Maybe the sample size is 50, maybe the sample size is 100, whatever the sample size is, you're going to create a normal distribution out of it. And it's just really, really important to understand that's what we're creating with this. And we're going to be seeing sampling distributions for proportions today. But first, we're going to do what we didn't do yesterday, which was our progress. We took a test on Monday, and I still need to grade that test, but I will be putting that in. All right, so notice that we have made it all the way down here. This is looking like progress. Remember, we're just going as far as Separation Canyon. And look at that, beautiful Elves Chasm. We're going to do something a little different today. I'm going to show you a picture. No, this is a video of it. I'll just really quickly show this. We won't watch the full thing. Taking a sweet time. There we go. You can see this beautiful waterfall. We're just going to call that good. So Ell's Chasm is a wonderful waterfall in the canyon. We've made it that far, guys, metaphorically. And now we're going to continue with Unit 7, sampling distributions. Okay, well, I had a slide for the midterm, but we already talked about that. Okay, so I'm going to put this link right here. I'm going to put it in the chat, but don't go there right away because you will be going there in a second. So we're going to suppose that we have a huge bag of Reese's Pieces. It has 1,000 pieces in it. And it says exactly 40% of the candies are orange. If we select a sample of 50 pieces, how many will be orange? And a random variable x, because it's going to be a different number each time, perhaps. But we're going to let our random variable x equal the number of orange candies in the sample. And what type of probability distribution is this going to be? So just looking at the problem, are we talking about a binomial or a geometric probability situation? So you got to focus on the N or the F right there, if you remember what those stand for.
Probably geometric, because we're not replacing what we took out, right?
We're not going to replace. And I'm glad you brought that up. That actually doesn't mean it's going to be geometric. But what it does mean is that technically, this is not going to be independent, and technically it's not the same probability. So in a technical sense, we have violated these two. So you could say it's neither. But this is where the large counts condition comes into play. So we can say there's 1,000 pieces, and if we're only, or sorry, this is where the 10%, not the large counts. This is where the 10% condition comes into play. If we're only pulling 50 from 1,000 pieces, we can treat this as though they are independent and that they have the same probability. All right. So if we changed our probabilities to account for the changing probabilities that happen because we're not replacing. So if we compensated for that, it would change our probability by a little, but not by a lot. All right, so anyways, knowing that we're good with that, are we looking at a binomial or a geometric setting?
Binomial.
Binomial. So what is it about binomial? This can be, Lily, it can be anyone. What is it about this that makes it binomial?
It's only one trial?
Well, you're on the right track, but it's more than one trial. Or I know what you're saying. We're pulling out 50 one time, but we do. All right, what does this N mean? Let's just talk about that.
The number of trials.
Number of trials. We have a set number of trials. In this case, it's how many?
50.
50. There we go. So essentially the question is, how many successes will we have out of 50 trials? And it's okay to use binomial for this because it is binary. It's either orange or it's not. And we've already talked about if it's independent and same probability. Essentially, it will be because it's less than 10% of the population. And then now we have a set number of trials, so that makes it binomial. Okay. So let's go ahead. I'm going to open this up real quick. And I want to show you how this applet works. Okay. So we said there's a probability of 40% that it's going to be orange. So when you go there, it's probably going to preload it as a 0.5 probability. So you want to change that to 0.4. And then we're taking a sample of 50. And we just want to do one sample real quick. How many do we get? So we can just draw the sample right here. And this, you can choose to animate it or not. But it just goes through and it pulls random ones. It has its own algorithm. So we got 19. So we might get 19. You might get a different number. All right. So what I'm going to do, let me come back to this. So if I present this again, you have the link. What I want you guys to do, and luckily this is something that's automated, so you can do quite a few of these. But I want you guys to draw a sample using that link and then determine how many pieces are orange. You don't have to share that with me right away. It says repeat this 5 times, but if you want, you could do this 10 times, okay? Because all you have to do, I'll show you what, and we're gonna record our results on the next page. So if you did this 10 times, all you have to do is come to this right here, and it says how many times you wanna do this, just type in 10. So 0.4 with a sample size of 50, you get 10. I'm not gonna animate this. And there we go. It automatically did 10 of them. And right here, the blue thing doesn't matter, but down here, you can see the dot plot that shows what results I got. So you can kind of figure that out. So I got a 12, a 15, 16, a couple 17s, and so on. So I want you guys to do this and get 10 results, and then you can go ahead and plot them on the next page. I will just bring this up so that you can add your dots to this whenever you are ready. Okay, so if you are still adding a few dots, that's good. And I know this isn't the most perfect dot plot that we could create, but we can still get a general idea. I mean, the lowest we ever got was 12, the highest we ever got was 28, and it seems like we're centered, well, we're centered around 20, it looks like. And that hopefully makes sense to everyone. We had a sample size of 50. We had a probability of 0.4. So we already talked about it with our binomial that the mean for this random variable is going to be n times the probability, which in this case is just that, which should be 20. So it makes sense that we're going to average around 20. In the long run, we're going to get that. Okay. So this still all checks out and we're good. I'm actually going to probably leave the dots on here because we're going to look at this again in a second. This might not work out when I do the dots, but I think we can still look through them. Okay. So what's the mean and the standard deviation for the distribution of X? We learned this yesterday. All right. So we have an average amount, right? This is 20. Right here. Now, we don't need to actually worry about the specific numbers because we can look at, well, let me see here. We've got our mean is going to be 20. And then for the standard deviation, this is a sample. And so if we knew the population standard deviation, then we could divide that by n. Now we can figure this out. Actually, what I want to do is let's just skip the standard deviation for now, because we're going to figure out a way of working through this whenever we convert this into proportions, okay? Because we're still looking at the raw count. We got, in this column, we got 20 successes. In this column right here, it was 28 successes, and down here is just 12 successes. So we've got a raw count, but what we want to do is we want to convert this into proportions. And proportions, of course, are decimals and values between 0 and 1. So we're going to convert this into proportions. And how can I convert this into a proportion? Like, what will I do in this case? So what proportion of my sample is 20 successes?
%.
40%. And how do we find that?
Just 20 divided by 50.
There we go. I can divide by the sample size. So in this case, 20 divided by 50 is going to be 0.4. So this represents 40% as a proportion. And now when we have 28 up here divided by 50, well, what is 28 divided by 50? So that's 0.56. And if I go down to 12, because that's what the lowest was, I'm not going to worry about all the different numbers. 12 divided by 50 is 0.24. All right, so those are our proportions. It goes anywhere from 0.24 as a proportion up to 0.56, but it averages, we can even see from our data, it would probably average really close to 0.4 as the mean of all these samples that we took. And this right here, this sample proportion is called p hat. It has a specific name, and we're going to see this quite a bit. But basically the sample proportion, just think of that. So how do we do it? We already talked about that. We divided by the sample size. And okay, this didn't quite work out perfectly, but if I erase all this, notice that the dot plot doesn't change. So I'm just going to get rid of this real quick. So it's close, but not exactly perfect here. But look, this is essentially the same dot plot. And notice that this was the 20 right here, and it lines up with the 0.4. And down here, this is the, so you can see it's not actually lining up perfectly. But it's okay. We can still get the idea that just by converting our 20 right here into a proportion of 0.4, by doing this, we have not changed anything about the shape of the distribution. But we can figure out the standard deviation and the mean of this sampling distribution of proportions. All right. So let me go ahead and clear all these dots off now. And that was the whole point, that we can still get that sort of thing. And all right. So now we're going to find the new mean and the standard deviation. All right, when we were thinking of this, no, I didn't want that. No, oh my gosh, I cannot get this right. There it is, I'm sorry. When we were looking at the mean and the standard deviation before, we've got the mean of this for a proportion is when we look at our binomial distribution, the mean of a binomial distribution is just the population mean, or technically it's n times p. So I'm kind of jumping ahead a little bit, and it's not the population mean. Anyways, it's n times p. The standard deviation for a random variable when we have a binomial is the square root of n times p times 1 minus p. Now, that was our binomial distribution where we were counting up the number of successes. That was before we turned it into proportions, okay? So when we converted this into proportions, here's what we did. We divided everything, just like Lily said, and just like you guys were thinking at home, we just divided everything by the sample size. I took my 20 successes and I divided it by 50, and that gave me my proportion of 0.4. Okay, so if I'm just dividing everything by the sample size, this is the upshot of all this. I'm going to take this and I'm going to divide the mean now. So the mean of a sampling distribution of proportions is just going to be n times p divided by the sample size, which is what we did. Again, I want to make the connection why we're dividing by the sample size. That's all we did a second ago. So when I divide that, it just becomes the proportion. So it all cancels out. So if I get rid of all this, it turns out that the mean of my sample proportion sampling distribution of sample proportions is just the same as a population proportion. Really straightforward. And luckily, this is a formula you don't have to have memorized. This will be available to you. Now, I'm going to do the same thing over here. I'm going to divide this by the sample size as well. But what I want to do is I want to put this underneath the all one radical. So it's going to be n times p times 1 minus p. And when I put the n under the radical, I have to square it. So that's n squared. So if you're following with this algebraically, this is what it looks like so far. And now I've got n in the numerator, n squared in the denominator, so I can cancel out that. And I get a final answer of p times 1 minus p divided by n, all under a radical. And the important takeaway from this, and this is what I hope you guys are thinking about, is that our standard deviation here is inversely related to our sample size. As this number gets bigger, as sample size gets bigger, our standard deviation for a sampling distribution of proportions goes down. So this kind of rings true when we talked about this yesterday. So if you have your population of proportions looks like this, but then you take a sample and you get a sample size 50, and what's the proportions there? This is also going to get more and more narrow. So the sampling distribution is this one that's more tightly compacted around the mean. The population might be more spread out. Okay. So that's kind of the derivation of those formulas, and there they are right there. That's what it looks like on your AP formula sheet. So you can see the mean of a sampling distribution of proportions, sample proportions, p hat, equals just the population proportion. The standard deviation of a sampling distribution of sample proportions is this formula right here. And we just found that by dividing the binomial numbers by the by n. And this, we can compare those to the mean and the standard deviation that we found for sampling distribution of sample means yesterday. And we can see that there's a lot of similarities here. We're just basically taking the standard deviation and dividing it by the square root, or we're dividing it by n. Same thing here. We're dividing it by the square root of n, but it kind of works out with the same logic. So as sample size gets bigger, just in general, as sample size gets bigger, standard deviation decreases. And I hope that point is very, very clear for you. All right, we're almost done for today. Let's see what this one is. What's the shape of this sampling distribution?
Is it just a bell curve?
Yep, and specifically, what kind of bell curve? Since we learned in bell work that there's multiple kinds, what kind is this one going to be?
It seems pretty normal and symmetric.
There it is. And that is a key idea. And I do want to draw a distinction between what we did when we went to that applet and we created a bunch of samples and plotted them. That is not a true sampling distribution. A sampling distribution represents every possible combination, and we model it mathematically. We have the mean that we have a formula for. So if this is a bunch of proportions, p hat, I could figure out the mean of this just by finding out what the population proportion is. And then if it's got a standard deviation, well, I don't actually take an infinite number or a vast amount of samples to figure out what this is. I derive it mathematically. I can say, oh, well, the standard deviation for this distribution of all possible samples and sample proportions is going to be the square root of the population proportion times 1 minus the population proportion divided by the sample size. So I drew a sample size of 50, it's a 40% probability of success, and I can just mathematically derive this. So luckily we have the shortcuts, but what we did when we just individually did trial after trial and simulation after simulation, that is, I believe we call those, I always forget the term exactly, but I believe it's called a randomization distribution or something to that effect. And that's if you have a limited number of simulations, but that's not really something you need to know. The key thing is that we're dealing with sampling distributions, which is a model of what every possible sample would look like that could be drawn from the population of size n. All right, and I believe this is where we're stopping for the day. It's actually not that much. We just wanted to derive a couple of formulas. And these formulas, like I said, are available for you. You do not have to have them memorized. And let me just jump ahead one. Oh, yeah, sorry. I believe, okay, I wanted to stop here. I didn't want to do central limit theorem today. We're going to start with that tomorrow. So this is actually the last question. I'm sorry, you thought you were about to get to go. All right, so here's the kind of question we can answer. Suppose we know that a bag of Reese's Pieces contains exactly 40% of them are orange. And if we select a random sample of 50 candies, what's the probability that the sample proportion will be 45% or greater? So luckily we have a population proportion that's given to us, and we need to figure out what this sampling distribution is going to look like when we pull out a sample of 50 candies. All right, so maybe take a second. I'm just going to put the formulas up here. And let me, so I'm not going to put up the formula for the mean. I'll put up the formula for the standard deviation of the sampling distribution of sample proportions. And I want you guys to just tell me what the answer is going to be once you've calculated it. So I'll just leave those blanks next to the equals and you can fill those in. Okay, so I want to look at this real quick. When it gives us this 40%, this right here is the population proportion, because it tells us that there's 40% that are orange. So luckily this is one, when we're looking at the mean, we don't even need to calculate anything. We can just say, oh, it's 40%, so 0.4. So that's kind of a takeaway. We're going to do some practice problems with this and with means tomorrow, but and we'll also look at that more on Monday. But hopefully you can see right now that when it just gives you the population proportion, just say, hey, there's the mean of my sampling distribution. It's going to be 0.4. Now we had to plug these numbers in, and so this, I'm just going to reverse engineer it and show the numbers, and that is correct. 0.4, 0.6, when you do 1 minus 0.4 over 50, that's what I plugged in here so that I could find the standard deviation of this. So now what we've ended up with is a bell curve, a normal distribution specifically, that has a mean of 0.4, a standard deviation of 0.069. And let me see, I've got, so my normal distribution, I could describe it this way, 0.4, 0.069. And now I can come up with the probability of getting a sample proportion of 45% or greater. Remember, I want to keep emphasizing this. Every single point that makes up this distribution is a result of a sample proportion. So you took 50 from this population randomly, and maybe you get 38% orange. And then you put it back, you get a different sample of 50, and then you get 43% the next time around. So you just keep doing this, all the possible combinations of 50 candies, and that's where we have, in this case, it would be, let's say there's 1,000 candies in the bag, it'd be 1,000 choose 50, which would be so many samples. If you remember, that would be millions and millions of samples. So we just mathematically model that. So what's the probability that one of those that we pick is going to be 45% or greater? Well, let's figure that out. So I'm going to come up with a z-score, which is going to be my 0.45 minus 0.4 divided by the standard deviation of 0.069 which gives me a z-score of 0.722. And my number might round a little differently because I used the exact value instead of the rounded off 0.069. But you should be in that range. So this is basically saying this 45% is going to live about right here in my normal distribution. 0.722 right there. So I can figure out what's the probability of getting that result or greater. Okay, and this is just going to be our normal CDF calculation. Because it's a normal distribution, that's what we were able to create. I just put 0.722 in and go from there to positive infinity. There's about 23.5% chance. And if I'm going too fast, if you're getting lost in something, let me know.
Wait, so what did you enter into the normal CDF, like for like the sigma and then the mu?
That always stays as 0 and 1. So the mu is 0 and the sigma is 1.
Okay.
Yeah, that's the
Okay,
standard, that's normal.
And then for the lower, you entered the z-score, and the upper was just the like infinity.
Yeah, and I always just put 99 in because that's going to be good enough. But you can
Okay.
type in 99999, you know, as far as you want.
Okay.
Okay, so I want to wrap this up by showing that this is the sampling distributions. I know I've already said this, but this is the heart of what we're going to get into when we do hypothesis testing and statistical inference. So you've heard about things like if something is statistically significant and, oh, we got a p-value. We're going to talk about p-values eventually. Okay, so this is stuff that you've probably heard these terms. Maybe you have familiarity with it to some degree. This is the heart of it. And the basic idea is the same kind of question we just asked. If we took a sample and we got 45% of these 50 are orange, is that something that we would expect by random chance if there's 40% in the bag? And we can say, oh, there's a 23.5% chance. Okay, that's actually not too unlikely. It's not certain, but it's not unlikely. And we have kind of different cutoff points where we decide, is this unlikely enough? And I'm jumping ahead a little bit. I just want to plant the seed that this is the heart of it. We're always going to be taking a sample or looking at data that came from a sample and deciding, is this proof that maybe this claim is true or false? What's the likelihood of getting this result? So if you can understand how sampling distributions are created and what they're signifying, then you're going to have a leg up when we get into inference testing or hypothesis testing, statistical inference. All right, I do want to stop it here. We're not going to jump into the rest of it, and we're going to do some more practice problems tomorrow. So no homework tonight, but we'll continue with this tomorrow. And remember, your midterm is on Friday. All right, so with that, if you have any questions, please stick around. Otherwise, have yourself a wonderful day, and I will see you tomorrow.